Alright, so the first three videos we were talking about deals with, the first four videos was just a matrix review today, or not today, but now we're going to continue on actually applying this to differential equations. So, say now we have a system of linear differential equations. So here we have a system of linear differential equations. The first one's going to be the dependent variable of x, the second one's with a dependent variable of y, and the third one's with a dependent variable of z, all having functions of x, functions of y, functions of z, and then functions of t, which is going to be the independent variable. All right, that independent variable could also be a constant. And so what we're going to focus on today is we're going to focus on, looking at solutions to a system of differential equations. So here's just an introduction. We have a system of linear differential equations. Now, this could be written two other ways. I decided to, give you this so that you can see, okay, we have a bunch of different variables in our system, a bunch of different dependent variables, but they all correspond to one independent variable, which is with t. And so here, it's the same thing. What I've written is the same thing. This can continue. It doesn't have to be a system of three differential equations, so that's why I have that ellipsis there. This can go on to 26 different first order linear differential equations. But I'm just saying, I just have that there because it could be greater than just three different dependent variables. So again, this is just the same thing of what's above. It just has, instead of saying x, y, and z, it has x sub 1, x sub 2, x sub n, showing that, okay, we have a different dependent variable each time we go through. One's of x sub 1, one's of x sub 2, one's of x sub n. Alright, and then again, this right here is also the same thing. Alright, but this part right here is just the first part expanded. Alright, again, these are all going to be functions of dependent variables x. The first one's going to be like of x, what we had up here. Then it's going to be of y, it's going to be of z. And then, again, they're all also going to correspond to that function t. So let's go ahead and talk about how we can put these in matrix form. So the first thing that we're going to do is we're going to notice, okay, we have a system of linearly first order differential equations, and the first thing that we're going to do is make sure that we grab all of our different variables. So x is going to be the variable matrix, making sure that we denote all of our different variables, all of our different dependent variables, A is going to be our coefficient matrix. We're going to pull all the coefficients of all the dependent variables into one matrix, and then f of t is going to be any part of our differential equation that does not have the dependent variable. So it could have the independent variable t, or it could just be a constant. That's going to be your matrix f. Alright, so what we can do is then we can write our system of differential equations into x prime, which is the derivative, a, which is the coefficient, x of all the different variables plus anything that remains. All right, now again, that anything that remains, if there's no f, then we have a homogeneous differential equation. So we're going to write the linear system in matrix form. So here we have what we want to write in matrix form. Notice there are no functions of t, there are no constants, so it's homogeneous. Now, we first want to denote what is our dependent variables. We have x, we have y, we have z. So we're going to make a matrix of x, y, and z. So we made matrix x to be x, y, and z. The next thing we want to do is find our coefficient matrix. And so now let's go ahead and find A. Notice that that first matrix, that first differential equation has 1x minus 1y plus 0z. So it's 1, negative 1, 0. The next one's going to be 1, 0, 2 because we have x plus 2z. There's no y. And then we have negative 1, 0, 1. That's negative 1 plus 0. And it's negative x plus 0y plus 1z. So that's why we have negative 1, 0, 1. Then we're just going to put this into our matrix form. X prime equals x x prime equals ax, and we're just going to write out what a is. We don't have to worry about writing out what x is because that's just our dependent variables. Alright, so that's how to put it in matrix form. So when I ask you on your homework, put this in matrix form, that's all I'm going to have you do. Alright, solution vector on an interval I is any column matrix X whose integers are a differentiable function satisfying the system on the interval. So now I'm going to give you a solution, and I just want you to verify that we have a solution. That's all this is. So we're going to start off with our system of differential equations. We're going to put that into matrix form. So notice that we have x, y as our dependent variables, so that's matrix X. We have our coefficient matrix, which is -2, 5, -2, 4, again corresponding to just our coefficients. And then we have a solution. It says that our solution is matrix X. So if this is a solution, let's first go ahead and write this as the matrix. So that e to the t, it's a scalar, so we just multiply all of our elements in our matrix by e to the t, so that's what I did first. Then we're going to go ahead and, because this is a solution to the differential equation, we're going to take the derivative of x. So we start with x prime. So go ahead and I take the derivative of 5 cosine e to the t. Alright, that's going to be a product rule. So we're given, -5 e to the t sine t plus 5 e to the t cosine t. And then we're going to take the derivative of the second element, which is going to be -3 e to the t sine t plus 3 e to the cosine 3 e to t cosine t minus cosine t e to the t minus sine t e to the t. I'm going to clean that up, the last element, and then we're just going to get 2e to the t cosine t minus 4e to the t sine t. All right, so now once we verify, okay, this is our derivative of x, when we do the actual matrix multiplication, when we do ax, we should get x prime as our solution. So we go ahead and we put in our a and we multiply it times our x. So we said this was the x because we said that was a solution, and then we said that this is our matrix A, and then now we're going to go ahead and multiply. So we multiply the two, and we get that. Again, we're allowed to multiply because we have a 2 by 2 times a 2 by 1, middles match, so we're going to get a 2 by 1 matrix. And then we multiply. After we multiply, we notice, oh hey, we get 5e to the t cosine t minus 5e to the t sine t, 2e to the cosine t minus 4e to the t sine t, which matches with that. So it is a solution.